Okay, hello everyone, welcome back. Now we're gonna see the presentation of Roberto. So, Jose, you can go.
Yeah, sure. Hello, everyone. Today I'll be talking about R-square gravity and its potential application to dark matter. Uh, so I'll be going over two papers. This one from Sembranos, it's from 2008. It's a bit old, and this one from 2021. It's from Yuri Shtanov. Let me start with the Sembrano one, the older one. All right. So basically, the idea is that so we have reasons to extend Einstein's gravity, different reasons for normalization reasons, and well, nothing tells us that the Einstein-Hilbert action and Einstein's field equations are the ones that actually describe the full thing. It might as well be an IR theory, and we need to find a UV theory. So one very straightforward extension to it is if we introduce other powers of the Ricci tensor or Ricci scalar. So you could introduce in general not only the Ricci scalar in tensor, you could introduce the Riemann tensor, but there is so basically there is a constraint that allows you to only introduce the Ricci tensor in the scalar. But in here we will talk about the Ricci scalar only in R-square gravity. So when you introduce this, okay, I think, do you guys see my screen?
Yes.
Okay, good. So when you introduce the Ricci scalar, so you get dark energy like cosmological constant, and you have the usual Einstein-Hilbert action here. And then you can introduce a new power of the Ricci scalar and several others that are UV corrections to your theory. But I won't care about those. I care about this one. And well, when you introduce like the Ricci scalar square, you get other powers of the derivatives of the metric. So the Ricci scalar has a derivative in the Christoffel symbol, and the Christoffel symbol has a derivative in the metric. So you get like second order derivative in one Ricci scalar. If you get square, you get other orders of derivatives. And the fact that you have different orders of derivatives, you basically include a new degree of freedom in your theory, and this degree of freedom will be a scalar. Okay, and then you can, for instance, include this term here in front of the Ricci scalar square. It has to be dimensionless because this term has dimension 4, and then you have to put the dimension 0 term here, and this number is, well, a parameter chosen by the author. I have no idea why he put 12 here. You see that the other author puts a different number. But generally you have like this m Planck square over m0 square, and then this m0 square is the mass of your scalar, and this paper is interested in this scalar being dark matter and the consequences of it. So how do you see the scalar appearing? This is the equations of motion, okay? This is Jordan frame. In order for the scalar to appear, you have to go to Einstein frame. So you perform conformal transformation. So he does the conformal transformation a little bit different than we usually do. We do it with an explanation, but you just can see that this is like a limit on the fact that phi over m blank is really small, so the explanation just becomes this. And you have linearized gravity with the usually traceless tensor H mu, and this will be like the 2 degrees of freedom of the graviton, and you get this new degree of freedom, new scalar degree of freedom here. And then this would be, in principle, the conformal transformation that you perform to go from the Jordan frame to the Einstein frame. And then in the Einstein frame, you have just Einstein's gravity, gravity is decoupled, and everything is fine. And then this accounts for the fact that the geodesics in both frames would be different. So basically, once you do this, this is very, this would be GB mu hat, just is the background field to be Minkowski, for instance. So if you have expanding FLRW metric. Okay, so you do this. Hi.
We have a question here from our audience.
Hello.
Yeah, say. Hi.
This new J, this new G you are considering are just the Minkowski metric or no?
Yeah, in their case, they don't explicit, but by the Feynman rules they get, probably it is the Minkowski metric.
Okay, because probably you are considering that this h is every term of order of h squared is going to be 0, probably in the calculation.
H here, yeah. So
Yeah.
This they do linearize gravity alongside the conformal transformation.
Okay. This is new conformal transformation for me, but it's interesting.
Well, Matheus, this is basically what we did essentially, because you only get what the coupling we do with this type here, doing this, because this is essentially the explanation, but this is just one term of the explanation.
Okay. So it's okay.
No new.
Yeah.
Well, let's go. Where was I? Okay, so basically, if you do this, it's pretty clear that the action will depend on this new metric, G mu nu, that has this little thing here. And, well, the coupling then comes from the trace of the energy momentum tensor from the metric. Basically, this will be the coupling of it. How you see this is basically the answer for everything physics. The other one, because the answer for everything physics is harmonic oscillator. The other answer is Taylor expansion. This one is Taylor expansion. So basically, this is the trace of the energy momentum tensor. You have like some sort of like non-conformal things because you have mass for the guys in the Lagrangian. This is the Higgs mass, and you have mass of the fermions, mass of the W, and mass of the Z bosons. In general, you don't have mass for the photon and the gluon, but there's something called conformal anomaly, which you can just basically understand that the beta function does not disappear. And then you also can get the coupling with photons. So you have here the coupling of the phi particle with photons. And this is very interesting because we can do a bit of freenode with this coupling. I will not care very much about this one. And then the CEM here is just the integration of the loop factors that you get in order to get the actual coupling. So let's go. So one of the things they do is abundance. So this is, well, I will not do this introduction to the other paper because it's basically the same stuff you get. The only difference is in the other paper, before I go to the pheno, I will introduce a little bit, is that they assume that the fields in the standard model also transform into the conformal transformation, each with its own factors depending on the energy of them, on the dimension of the field. And the only part of the action that will not transform properly is the Higgs action, and then you get a coupling with the Higgs. This is a bit different because you usually get that type of coupling with the energy momentum tensor, but once you do this conformal transformation here, you see this is the conformal of Matheus, and then if you Taylor expand this, you get that thing there.
Okay.
So basically, they get, where was I? Coupling with the Higgs. This is the difference, the main difference, and then you get a difference in how it's produced and what can you detect. So let's go back to the other one. Basically here, you can produce it differently. What they assume is something I don't like very much, which is a misalignment mechanism. They assume that the field had some abundance first, and you only have interaction with the thing. So they put here in terms of the number density of the field and the entropy of the universe, so it dilutes depending on how entropy evolves. This factor only accounts for entropy. Hi.
Hi, I just have a question. If they are using misalignment mechanisms, they are producing a kind of like similar to the Axon field or something like that?
Well, I'm not sure because this is not a pseudo-scalar.
No, it's okay. I was asking this because when you're using the misalignment mechanism, it is usual to have a kind of Nambu boson-Goldstone. So that's why I was asking this. They are including, or they are just using
No, it's just a regular scalar, and the misalignment mechanism can be used as a regular scale for a regular scalar. They're just saying that initially the field was not in its minima; it was somewhere else in its potential. That's basically what they say. So it's
okay,
sort of,
they are using this kind of feature, and that's all.
yeah, that's why I don't like it. It's very fine tuning for me. And then
Okay, thank you.
this is what they do. So you mention axes here. So it's not in the minimum, and Well, at some point you have like that the Hubble expansion is around the mass of the scalar, and then it starts to oscillate and behaves as a standard scalar, and this oscillation is the dark matter particle, the cold dark matter particle. So basically here they feed some things, and then you get this. This is around the pheno you can get about it. This is around, in order to get the dark matter abundance, super dark matter abundance, you have to have these values of the misalignment pair. This is the misalignment field, phi 1, and M0. This is just standard model. Okay, this is the idea. And what you get is actually that the perturbation on the background metric is small enough that it's in reasoning with the expansion in the exponential. So one sign sigma you can have, it's a scalar, has mass. Fifth force, you have Yihawa potential of some sort, depends on the masses, and on the mass of the scalar. Of course, this is the length of the range length of the interaction. And then they found this bound here by the Tosher balance experiments that M0 has to be greater than around 10 to the minus 3 electron volts at 95% confidence level. This is very light scalar, very, very light scalar. And then they do a search in the 511 keV line flux, okay, on dark matter. So they first do by considering annihilations into electron positron, because we know that this 511 keV line flux, it must come from a positron somehow, like happening in the well, don't remember the name of the part. Oh yeah, the galactic center. So they do the pheno here. They consider the decay by considering the coupling of the phi 1 standard model. Basically it. See some things, and they also look for gamma ray lines by considering the 2-photon decay from that coupling you have there above on the paper. That they put here the gamma, and you see that everything has a relation with M0. And we also have a relation with phi 1. All right, someone asked me. Okay, hi.
I was sorry. I was just asking if they have a kind of calculation for do the limit of the zero detection with, for example, CTA, Hales, Fermi.
No, they don't do with CTA.
Because in this case, it would be nice to have this kind of vincul. Because it is easy to have this kind of calculation in a paper for us. But we need to know what is the range of energy and see, calculate, of course, the spectrum.
Yeah.
What is the coupling with other particles with this kind of scalar? For example, they can couple just with charged particles, or how will be this?
With what? I'm sorry?
Charged particles?
Yeah, they couple depending on the trace of the energy momentum Samson diode here. They couple universally, basically the coupling. Of course, it depends on the mass, but the idea is that since this comes from gravity, you have to have that. I forgot the name of the principle. It's a principle that since gravity has to act equally on every single particle in the universe. Of course, depending on the mass, but generally the weight of the interaction is the same. So you have this factor of mass blank here below, so it's very suppressed. But this is coupling with the particles of the standard model. You do have coupling with charged particles. You can produce them. And yeah, something I considered, Lucia, doing is calculating the cascade. But one thing is that it's a very good question you ask, is that the range of mass you have here for the range of the abundance that you need to the misalignment term here. You have to, they do the phenomenology with these two guys. For CTA, this is not usually, you get like only this part here, and you can see that it's already severely constrained due to the 511 keV line they have. But it would be interesting to see if you can extend it, because the CTA goes from 10 to the 2 GeV, 10 to the 5.
It's like a 500 GeV until 100 TeV.
Yeah, 10 to the 5 GeV, yeah. It's already here. So it's a lot is already excluded. I would have to check. We would have to do the calculation to check if you can extend and move this.
We have, we actually, of course, we do internet detection, for example, with high energy telescope, for example, with the CTA, but we also have some experiments, for example, the COSI, that is in the NASA. It's an experiment of NASA. It evaluates a kind of low energy social MEV, for example. So it would be interesting because it would be included in this kind of study. And it is easy to do a kind of for do the calculation to that.
Yeah, sure. Do they give us a bounds on the lifetime of dark matter already? Because if they do, I already have the gamma ray spectrum generated from general decays on the masses. I have the code. I can just plug in the masses maybe. No, I haven't seen this experiment specifically. Yeah, it would be interesting to see something I'm seeing with Manfred. What are the possibilities? This is old. Maybe there are some new bounds here. This is from 2008. I think I can take a look and answer you. But the idea is basically, yeah, they do put bounds on gamma rays. Specifically, this one here is bound on gamma ray lines because it's the direct decay of phi into d photons. So it's a line, not a continuum like what I've done with Mateus in the continuum one because it's secondary and other types of photons. But yeah, it would be interesting to see.
Okay.
All right. Yeah. So basically, this is I think the plot of the paper where they exclude. So you have overproduction being excluded here, the line being exactly what you get for the dark matter abundance. Exclusion for gamma rays, you can have both from the, you see that the KDB 511 KDB line here is the most constraining one because you can get to 10 to the 9 GeV on the misalignment misalignment, I guess this is just misalignment, the name of this thing. So, and then you have your color force here, it's this bound. This is why it's squared like this, because the bound is all in the mass. It has to be greater than 10, they're all the 10 to the minus 3 electron volts. So all of these regions are very excluded. Okay. Well, this is basically what they do in misalignment. And then the difference from this one to the other paper is that they do not postulate that it's a misalignment term. What they say is that since it couples to the Higgs, it will couple strongly to the Higgs. As you can see here, this is the quadratic quadratic you have from the Higgs and the scalar phi. It's mixed, so you have to perform a rotation basically, which is this is basically rotation in general. So put it into the diagonal form. And what happens is there's such a strong coupling of the Higgs here that the scalar, this is what they call, this is scalar graph, so it's scalar, it will couple so strongly that it will not oscillate. And then once you have electric symmetry breaking or electric crossover as they say here, what happens is that this term, which is the term that is relevant here, that causes this strong coupling, it will be diluted out, and then the field will be allowed to oscillate. And once it starts oscillating due to the coupling here around the minima of the potential, you see this is the minima of the potential before electric crossover, and we have like electric crossover happening, and then it starts oscillating, and then once it starts oscillating after electric crossover, it can behave like dark matter. And the only bound they put here is from the abundance, which they do like lots of calculation, just usual cosmology. You have here some adiabatic term for the oscillation of the field. And then they found, so simply, it's a little bit different because you had, in the old paper, you had one more degree of freedom to pheno, which is the misalignment. Here, they only put the mass, as you can see on the logarithm, the mass here, there you go, so you see that's a different term. It should be 3 times 6, 18, instead of 12. I don't know why they do it, but they do. So basically, this is the only term that's relevant in this area. So what they find is the mass has to be around a certain value, which is of order 10 to the minus 3 electron volts. Well, this is basically what the papers say, and since R-squared gravity is sometimes used as inflation, and you can see here they do reference it, because if it is, start on this inflation, the mass of the scalar element is already constrained to the 10 to the minus 5 Planck scale. They say that maybe inflation could be generated by the Higgs, but I'm a little bit skeptical about that because I think it's really, really constrained already as well. So, well, this is what I wanted to say about it. If you have any questions, please ask.
So, any questions? If not, I think we can end here. Okay.
Sure.
So, thank you, Jose. Let's thank the speaker again.
I think Lucia has a question. She raised her hand.
No, sorry, I just forgot to just put it down.
Okay.
Okay, so thank you guys. See you next time.
See you.
I'm gonna end the live here. I think it's